Hello everyone. Today we'll study more about linear systems and matrices. First of all, let's look at the theorem here. A system of linear equations may have no solutions, exactly one solution, or infinitely many solutions, and there are no other possibilities. Let's prove it. Let Ax equal to B be a system of linear equations in matrix form. Let Ax equal to B be a system of linear equations in matrix form. In general, we can write a system of linear equations in matrix form. So let Ax equal to B be the system of equations in matrix form. Then, for any system of linear equations, it may be inconsistent or it may be consistent. There are two possibilities. It may be inconsistent or it may be consistent. Inconsistent means there are no solutions. If a system of linear equation is inconsistent, that means there are no solutions. What if it's consistent? If the system of linear equation is consistent, means it has solution. It has at least one solution. At least one solution means what? At least one solution means it may have exactly one solution, or it may have more than one solution. Consistent means it has at least one solution. At least one solution means it has exactly one solution or more than one solution. Consistent means at least one solution, which means exactly one solution or more than one solution. So for any system of linear equations, we have these three cases. And here we can see that the first case, no solution, imagine the first case here. The second case, exactly one solution, imagine the second case here. The third case, more than one solution, it doesn't match infinitely many solutions. So here you can see that the first two cases matches, but the third case doesn't match. The third case doesn't match. So what's left for us is to try to prove that if there are more than one solutions, then it must have infinitely many solutions. If the system has more than one solution, then it must have infinitely many solutions. So in order to complete the proof, we need to show that if the system Ax equal to B has more than one solution, then it must have infinitely many solutions. Then it must have infinitely many solutions. We should show that if the system has more than one solution, then it must have infinitely many solutions. Let's prove it. First of all, let column vectors S1 and S2 be two solutions. Be two distinct solutions, means they are different solutions. Let S1 and S2 be two distinct solutions of the system AS equal to B. If they are distinct solutions, then we know that AS1 must equal to B. AS2 must equal to B. If they are solutions, that means if I plug in S1, I get B. If I plug in S2, I also get B, if they are solutions. And also, since S1, S2, they are distinct solutions, then S1 minus S2 is not 0. Since they are distinct solutions, S1 minus S2 is not 0. Next, let me introduce another column vector called x0. The column vector x0 be defined as x1 minus s2. Then x0 is not 0 because s1 minus s2 is not 0. Also, if I take matrix A times x0, what do we get? We know that x0 is x1 minus s2. If I distribute matrix A, I get as1 minus as2. And here, what's as1? What's as2? as1 is B. as2 is also B. B minus B is 0. So we have ax0 equal to 0. We have ax0 equal to 0. Next, let's consider another vector, another column vector. Let's consider another column vector. The column vector x3 equal to s1 plus kx0. The column vector s3 equal to s1 plus kx0. Then what do we get? Then if I plug in x3 into the equation, what do we get? If I plug in x3 into the equation, what do we get? as3 equal to a times s1 plus kx0, where k can be any real numbers. K can be any real numbers. What do we get here? If I distribute A, I get a s1 plus a times kx0. That's as1 plus k times ax0. as1 is B. ax0 is 0. ax0 is 0. B plus k times 0 is B. So if I plug in x3, if I plug x3 into the equation, I get B. If I plug in x3 into the equation, I get B. That means x3 is another solution of this equation. If I plug in x3, I get B. That means x3 satisfies this equation. That means x3 satisfies this equation. So x3 is a solution to the system of linear equations. Ax equal to B. If I plug in x3, I get B. That means x3 is a solution of this equation. And this is true for all k. This is true for all real number k. And since there are infinitely many real number k, since there are infinitely many real number k, then there exists infinitely many such S3. There exists infinitely many such column vectors X3. So the system of linear equations Ax equal to b has infinitely many solutions. That complete the proof. So if the system has more than one solution, it must have infinitely many solutions. That complete the proof that a system may have either no solution, exactly one solution, or infinitely many solutions. And there are no other possibilities. Next theorem, let A be a n by n matrix. If A is invertible, then for each n by 1 column vector B, there exists a unique solution to the system of equations As equal to B. So this theorem says if A is invertible, then for each n by 1 column vector B, there exists a unique solution X to this system of equations. Let's prove it. The proof will take two steps. We first of all show that for each B, there is a solution X to this system of equations. Next, we show that the solution must be unique. So it takes two steps. First of all, let's show that there is a solution for each B. Since A is invertible, then inverse of A exists. Let B be an n by 1 column vector. In the equation As equal to B, if I multiply both sides by inverse of A, what do I get? I get inverse of A times Ax equal to inverse of A times B. On the left side, inverse of A times A, if we use associative law, I get inverse of A times X. I leave the right side the same. Take the left side here. Inverse of A times A is identity matrix. Identity matrix times X is X. So S equal to inverse of A times B, which means this equation has a solution. So the equation As equal to B has a solution. Inverse of A, it has a solution S equal to inverse of A times B. Next, we need to show that the solution is unique. Let column vectors S1 and S2 be two solutions of the system As equal to B. Since S1 and S2 are solutions of this system, that means if I plug in S1, it must satisfy this equation. When I plug in S2, it must also satisfy this equation. Then AS1 must equal to B, and AS2 must equal to B. Since S1 and S2 are solutions, that means when I plug in S1, AS1 must equal to B, and AS2 must also be B. Since both AS1 and AS2 they both equal to B, then they must be the same. So AS1 equal to B, and AS2 equal to B. they must be the same. Since they both equal to b, as1 must equal to as2. Next, I can multiply both sides by inverse of a. Next, I multiply both sides by inverse of a. Then, by associative law, I have inverse of a times s1 equal to inverse of a times s2. Inverse of a times a is identity matrix. Identity matrix times s1 is s1. On the right side, inverse of a times a is also identity matrix. Identity matrix times x2 is s2. So here we prove that s1 equal to s2, which means for any two solutions of this system of equation, they must be the same. So all solutions must be the same. That means it has only one solution. So the system of equations A is equal to B has a unique solution. Because every solution is the same, so it has a unique solution. Let's complete the proof. Next, let's look at an example. Let A be a 3 by 3 matrix. Find the solution of the system of equations A is equal to B for each of the following B's. Part A, B is the column vector 2, 3, 4. Part B, B is the column vector -1, -2, and 5. For each B, find the solution X. According to the previous theorem, we know that if A is invertible, then there's a solution S equal to inverse of A times B. So let's first of all find inverse of A. For inverse of A, we first of all write matrix A 2, 1, 0, 1, 0, 2, 4, 2, 1. Then followed by identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. For inverse matrix of A, we first of all write matrix A followed by identity matrix. Then apply row operation. Try to make A to be identity matrix. Once we make A to be identity matrix, identity matrix will be inverse of A. So let's first of all apply row operation, make A to be identity matrix. What we can do first, we try to make 1 here, so I can interchange row 1 and row 2. Interchange row 1 and row 2, I get 1, 0, 2, 0, 1, 0, 2, 1, 0, 1, 0, 0, 4, 2, 1, 0, 0, 1. First of all, make 1 here. In the first row, first column, make a leading 1. Next, try to make all entries below leading 1 to be 0. Try to make 0 here and 0 here. How do I make 2 to be 0? What I can do here is I can multiply first row by -2, add it to the second row. Multiply first row by -2, add it to the second row. I get 1, 0, 2, 0, 1, 0. 1 times -2 is -2. -2 plus 2 is 0. -2 times 0 is 0. 0 plus 1 is 1. -2 times 2 is -4. -4 plus 0 is -4. -2 times 0 is 0. 0 plus 1 is 1. -2 times 1 is -2. -2 plus 0 is -2. -2 times 0 is 0. 0 plus 0 is 0. Next, try to make 0 here. So I can multiply first row by -4. Add it to the third row. -4 times 1 is -4. -4 plus 4 is 0. -4 times 0 is 0. 0 plus 2 is 2. Negative 4 times 2 is negative 8. Negative 8 plus 1 is negative 7. Negative 4 times 0 is 0. 0 plus 0 is 0. Negative 4 times 1 is negative 4. Negative 4 plus 0 is negative 4. Negative 4 times 0 is 0. 0 plus 1 is 1. Now move to the second row. In the second row, try to make the first non-zero entry to be a leading one here. It's already a leading one. So try to make all entries above and below leading one to be 0. This is 0 here. On the bottom, try to make 0 here. So I can multiply second row by negative 2, add it to the third row. Multiply second row by negative 2, add it to the third row. First row stays the same. Second row stays the same. Multiply second row by negative 2, add it to the third row. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times negative 4 is positive 8. Positive 8 plus negative 7 is positive 1. Negative 2 times 1 is negative 2. Negative 2 plus 0 is negative 2. Negative 2 times negative 2 is positive 4. 4 plus negative 4 is 0. Negative 2 times 0 is 0. 0 plus 1 is 1. Then in the third row, try to make the first non-zero entry to be a leading one. It is a leading one here. So try to make all entries above leading one to be 0. So here I can multiply the third row by negative 2 and add it to the first row to make 0 here. Third row stays the same. 0, 0, 1. Negative 2, 0, 1. I get 1, 0, 0 in the first row. Negative 2 times negative 2 is 4. 4 plus 0 is 4. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 1 is negative 2. Negative 2 plus 0 is negative 2. Next, I can multiply the third row by positive 4. Add it to the second row. I get 0, 1, 0. 4 times negative 2 is negative 8. Negative 8 plus 1 is negative 7. 4 times 0 is 0. 0 plus negative 2 is negative 2. 4 times 1 is 4. 4 plus 1, 4 plus 0 is 4. Once I make matrix A to be identity matrix, identity matrix become inverse of A. So inverse of A here is 4, 1, negative 2. Negative 7, negative 2, and 4. Negative 2, 0, and 1. By the way, if A is not invertible, there are no solutions. There are no solutions for X. If this matrix we cannot make identity matrix, then A is not invertible. If A is not invertible, then there are no solutions for HB. Now, since A is invertible for inverse of A, then for HB, S is equal to inverse of A times B. So for part A, S is equal to inverse of A times B. Inverse of A is 4, 1, negative 2, negative 7, negative 2, 4, negative 2, 0, 1. Matrix B is 2, 3, and 4. Then multiply. Take row times column. 2 times 4 is 8. 3 times 1 is 3. 4 times negative 2 is negative 8. 8 plus 3 minus 8 is 3. Next, row times column. 2 times 7 is negative 14. 3 times negative 2 is negative 6. 4 times 4 is 16. Negative 14 plus negative 6 is negative 20. Negative 20 plus 16 is positive negative 4. Next, the third row. Row times column. Negative 2 times 2 is negative 4. 3 times 0 is 0. 1 times 4 is 4. Negative 4 plus 0 plus 4 is 0. So when B is 2, 3, 4, the solution is -3 is 3, -4, and 0. For part B, do the same thing. X is inverse matrix of A times B. Inverse matrix 4, 1, -2, -7, -2, 4, -2, 0, 1 times the matrix times the column vector -1, -2, and 5. Multiply. Use row times column. It's -4, -2, and -10. -4 plus -2 plus -10 is -16. Next, row times column. It's +7, +4, +20. 7 plus 4 is 11, 11 plus 20 is 31. Next, row times column. It's 2, 0, and 5. 2 plus 0 plus 5 is 7. So when B is -1, -2, and 5, the solution is -16, 31, and 7. And for this problem, let me remind you one thing. We can also solve this problem using Gauss-Seidel Elimination. For the same problem, we can also solve it using Gauss-Seidel Elimination. If we solve it using Gauss-Seidel Elimination, we should get exactly the same answer. Next, let me remind you the Gauss-Seidel Elimination. So for Gauss-Seidel Elimination, we first of all write the augmented matrix. For the augmented matrix, write matrix A here, followed by the column vector B. Write matrix A first, then followed by the column vector B. Matrix A here is 2, 1, 0, 1, 0, 2, and 4, 2, 1, followed by the column vector B. First column vector B is 2, 3, and 4. Let's solve it. So, use Gauss-Seidel Elimination. We first of all try to make a leading one here. So I interchange row 1 and row 2. I get 1, 0, 2. 1, 0, 2, 3. 2, 1, 0, 2. Third row stays the same. 4, 2, 1, 4. Next, next leading one. I try to make all entries below leading one to be 0. So I can multiply first row by -2. Add it to the second row. I get 1, 0, 2, 3. That's 0, 1, -4. -2 times 3 is -6. -6 plus 2 is -4. Next, I can multiply first row by -4. Add it to the third row. I get 0, 2, -8 plus 1 is -7. -12 plus 4 is -8. Next, in the second row, try to make the first non-zero entry to be leading 1. It is a 1 here. Next, try to make all entries above and below leading 1 to be 0. This is 0, so don't change it. But this is 2 here. Try to make this 2 to be 0. I multiply second row by -2. Add it to the third row. You get 1, 0, 2, 3, 0, 1, -4, -4. Multiply second row by -2, add it to the third row. You get 0, 0. -2 times -4 is A. A plus -7 is 1. -2 times -4 is A. A plus -8 is 0. That's the leading one here. Next, we try to make all entries above leading one to be 0. So I multiply third row by -2. Add it to the first row. Here, leave the third row the same. I get 1, 0, 1, 3, 0, 1, 0, -4. So the solution here is x equal to 3, -4, 0. We get exactly the same solution. We get exactly the same solution for this B. Next, for part B, do the same thing. For part B, do the same thing. Write matrix A, followed by column vector B. Matrix A is 2, 1, 0, 1, 0, 2. Column vector B here is -1, -2, and 5. The third row in A is 4, 2, 1. So apply Gauss-Seidel Elimination. I first of all try to make leading one here, so I can interchange row 1 and row 2. I get 1, 0, 2 times followed by -2. Second row is 2, 1, 0, -1. Third row stays the same, 4, 2, 1, 5. Next, this is the leading one. I try to make all entries below leading one to be 0. So I can multiply first row by -2, add it to the second row. Multiply first row by -2, add it to the second row. First row stays the same, 1, 0, 2, -2, 0, 1, -4. -2 times -2 is 4. 4 plus -1 is +3. Next, in the third row, try to make 0 here. So I multiply first row by -4, add it to the third row. Multiply first row by -4, add it to the third row. I get 0, 2. -4 times 2 is -8. -8 plus 1 is -7. -4 times -2 is +8. +8 plus 5 is 13. Next, move to the second row. In the second row, try to make the first non-zero entry to be a 1. It is a 1 already. So try to make all entries above and below 1 to be 0. Above 1, we have a 0 already. So try to make 0 below 1. What I can do here is I can multiply second row by -2, add it to the third row. So first row stays the same. Second row stays the same. Multiply second row by -2, add it to the third row. I get 0, 0. -2 times -4 is 8. 8 plus -7 is +1. -2 times 3 is -6. -6 plus 13 is +7. Now move to the third row. We try to make the first non-zero entry to be 1. It is a 1 here, so that's a leading 1. Next, try to make all entries above leading 1 to be 0. So what I can do here is I can multiply the third row by -2, add it to the first row. Multiply the third row by -2, add it to the first row. Third row stays the same, 0, 0, 1. In the first row I get 1, 0, 0. -2 times 7 is -14. -14 plus -2 is -16. Next, I can multiply third row by +4, add it to the second row. Four times 1 is 4. 4 plus 4 is 0. I get 0, 1, 0 here. 4 times 7 is 28. 28 plus 3 is 31. So the solution here is this column vector -16, 31, 7. We get exactly the same answer. But if we solve this way, it looks like there may be too much work. We are reducing two matrices. It may be too much work here. If we observe the step, we can see that the steps are exactly the same. but we are doing the same thing twice. The step here is exactly the same, but we are doing the same thing twice. Can we make it a little easier by combining the steps together? Let's think of this matrix. Matrix A, followed by a column vector B from part A, and then followed by another column vector B from part B. Think of this matrix. In the first matrix, we have matrix A, followed by a column vector B from part A. In the second matrix, we have exactly the same matrix A, followed by a different column vector B from part B. So if I put these two column vectors together, I have one new matrix here. And then this matrix A is 2, 1, 0, 1, 0, 2, 4, 2, 1. Column vector B from part A is 2, 3, and 4. Column vector B from part B is -1, -2, and 5. Think of this matrix. That's the column vector B from part A. And this is the column vector B from part B. If I put these two column vectors together, and then reduce the matrices, what do we get? Try to use Gauss-Seidel Elimination. What I can do is I can make leading one here. So I interchange row 1 and row 2. I get 1, 0, 2, followed by 3 and -2. 2, 1, 0, followed by 2 and -1. Third row stays the same. Next, try to make 0 here, make 0 here. That's a leading one. Make 0 here, 0 here. So I can multiply first row by -2. Add it to the second row. Leave first row the same. 1, 0, 2. Followed by 3 and -2. I get 0, 1, -4. -2 times 3 is -6. -6 plus 2 is -4. -2 times -2 is 4. 4 plus -1 is 3. Next, try to make 0 here. I multiply first row by -4. Add it to the third row. I get 0, 2. -8 plus 1 is -7. -4 times 3 is -12. -12 plus 8. -12 plus 4 is -8. -4 times -2 is +8. +8 plus 4 is 13. Next, move the second row. Make the first non-zero entry to be leading one. It is a leading one here. So try to make all entries above and below leading one to be 0. Above leading one we have 0 already. So try to make 0 here. I multiply second row by -2. Add it to the third row. So first row and second row stays the same. Multiply first row by -2. Multiply second row by -2. Add it to the third row. I get 0, 0. -2 times -4 is 8. 8 plus -7 is 1. -2 times -4. -2 times -8 is -2 times -4 is 8. 8 plus 8. 8 plus -8 is 0. -2 times 3 is -6. -6 plus 13 is +7. Next, move the third row. Try to make the first non-zero entry to be 1. It is a 1 here. So that's a leading one. Try to make all entries above leading one to be 0. So I can multiply third row by -2. Add it to the first row. Third row stays the same. Multiply third row by -2. Add it to the first row. 1, 0, 0. -2 times 0 is 0. 0 plus 3 is 3. -2 times 7 is -14. Negative 14 plus negative 2 is negative 16. Next, multiply third row by 4, add it to the second row. I get 0, 1, 0. 4 times negative 4 is negative 16. 4 times 0 is 0. 0 plus negative 4 is negative 4. 4 times 7 is 28. 28 plus 3 is 31. So you can see that this is the solution we get from part A. This column is the solution for part A, 3, negative 4, 0. This is solution for part B, s equal to negative 16, 31, and 7. We get exactly the same solution, but solving this way is better than solving two matrices. The answer is exactly the same. If you compare the procedure, answer is exactly the same. But solving this way is easier than solving two matrices. So when we have two systems of equations, if the coefficient of the variables are exactly the same, if the coefficient of the variables are exactly the same, only write it once. Only write matrix A once, and then write the column of B's, write the column vector B twice. Write two different column vector B twice. Solving this way is easier than solving these two matrices. Answer is the same. And solving this way is even easier than using inverse matrix of A. Next, let's look at a theorem. Let A and B be square matrices. If the product A times B is identity matrix, then the product B times A is also an identity matrix. We know that in general, matrices A times B is not the same as B times A. In general, they are not the same. However, when the product of AB is identity, that's an exception. When the product of AB is identity, that's an exception. In this case, they are both identities. Now let's prove it. Let's prove it. In order to prove this theorem, I first try to prove that matrix B is invertible. Let X be a column vector. Consider the homogeneous system. Bs equal to 0. Consider this homogeneous system. If I can show that the only solution is the trivial solution, then by equivalence statements, matrix B must be invertible. Equivalence statement says all these four statements are equivalent. If I can show one of them is true, the rest must be true. If I can show that the homogeneous system AS equal to 0 has only trivial solution, then matrix A is invertible. So similarly, by equivalence statement, if I can show that the homogeneous system Bs equal to 0 has only trivial solution, then matrix B is invertible. So let X0 be a solution to the homogeneous system Bs equal to 0. Then, if X0 is a solution, that means if I plug in X0, Bx0 must be 0. From here, Bx0 equal to 0. If I multiply both sides by A, what do we get? I get A times Bx0 equal to A times 0. On the left side, by associative law, I get A times B times X0. On the right side, matrix A times 0 is 0. And by assumption here, we know that matrix A times B is identity matrix. Matrix A times B is identity matrix, so I got I times X0. Since I is identity matrix times X0 is X0. So I get X0 equal to 0, which means the only solution the only solution for this homogeneous system is 0. So the homogeneous system Bx equal to 0 has only the trivial solution. Since every solution is 0, it has only the trivial solution. Since every solution is 0, it has only the trivial solution. Then, by equivalence statements, matrix B must be invertible. By equivalence statements, matrix B must be invertible. Since B is invertible, the inverse of B exists. Since B is invertible, inverse of B exists. Next, we try to show that BA is also identity matrix. So start from here. We try to prove that BA is also identity matrix. AB equal to identity. If I multiply both sides by inverse of B, I get identity matrix times inverse of B on the right side here. On the left side, by associative law, it can be written as A times B times inverse of B. On the right side, identity matrix times inverse of B is inverse of B. On the left side here, B times inverse of B is identity matrix, and A times identity matrix is matrix A. So I get matrix A equal to inverse of B. Next, we try to show BA is identity. So I multiply both sides by B. I get B times A equal to B times inverse of B. And then on the left side I get BA. On the right side, B times inverse of B is identity matrix. And that complete the proof. If AB is identity, then BA is also identity. That complete the proof. Next, let me recall the definition of inverse matrix. Let A be a square matrix if there exists a matrix B with the same size, such that AB is identity and BA is also identity. Then we say A is invertible and inverse of A is B. That's the definition of inverse matrix. So, in order to show A is invertible, we must show that there exists matrix B such that AB is identity and BA is also identity. According to the previous theorem, we know that if AB is identity, then it's automatically true that BA is also identity. And similarly, if BA is identity, then AB is automatically identity. So, if we know one of them is true, the other one must also be true. So in the future, to show inverse matrix, there's no need to show both AB is identity and BA is identity. In the future, we show that either AB is identity or BA is identity. Showing one of them is enough to show both of them. So in the future, to show a square matrix A is invertible, we only need to show that there exists a matrix B of the same size such that either A times B is identity or B times A is identity. There's no need to show both A, B is identity, B, A is identity. There's no need to show both. Showing one of them is enough. Next, let's talk more about equivalence statements. Let A be a n by n matrix, then the following statements are equivalent. Last class, I showed you that statements 1, 2, 3, 4, they are equivalent. Which means, if one of the statements is true, the rest are all true. If one of the statements is false, the rest are all false. Today, I'll add two more statements. Statement 5 says, the system of equations AS equal to B is consistent for every n by 1 matrix B. And statement 6 says, the system of equations AS equal to B has exactly one solution for every n by 1 matrix B. So in order to prove that they are equivalent, today I'll prove statement 1, 5, and 6, they are equivalent. Today I'll prove statements 1, 5, and 6, they are equivalent. So I prove 1 implies 6, 6 implies 5, and then 5 implies 1. If I can prove statements 1, 5, and 6 are equivalent, since statement 1, 2, 3, 4 they are equivalent, use statement 1 as a bridge, we can show that they are all equivalent. So today I'll prove that statement 1, 5, and 6 they are equivalent by showing 1 implies 6, 6 implies 5, and 5 implies 1. Let me first of all prove 1 implies 6. Statement 1 says matrix A is invertible. So let me first of all prove 1 implies 6. Assume matrix A is invertible. Assume statement 1. Then we try to prove that statement 6 says the system of equations AS equal to B has exactly one solution for every n by 1 matrix B. Then, by an earlier theorem, says if A is invertible, then A be an n by n matrix. If A is invertible, then for every n by 1 column vector B, there exists a unique solution for the system of equations AS equal to B. That's all we need. That's statement 6. That's actually statement 6. There exists a unique solution to the system of equations AS equal to B. Then by earlier theorem, we know that for every n by 1 matrix B, which means a column vector B, there exists exactly one means unique solution. There exists exactly one solution to the system of equations AS equal to B. That's statement 6. By earlier theorem, statement 6 is true. Assume A is invertible. By earlier theorem, we know that for every n by 1 matrix B, there exists exactly one solution to the system of equations AS equal to B. That's the proof that 1 implies 6. Next, we try to prove 6 implies 5. So assume the system of equations has exactly one solution we try to show that the system of equation is consistent. Assume 6, proof for 5. Assume the system of equation AX equal to B has exactly one solution for every n by 1 matrix B. We try to prove the system is consistent. We know that if it has one solution, if the system has one solution, by definition of consistency, it must be consistent. Then, by the definition of consistency, if it has one solution, it must be consistent. That's by definition of consistency. So the system of equations AX equal to B is consistent for every n by 1 matrix B. That's by definition of consistent. If it has one solution, then it's consistent. If it has no solution, it's inconsistent. Since it has one solution, it's consistent. Next, try to prove statement 5 implies 1. So assume 1, proof for 5. So assume 5, proof for 1. Assume statement 5, proof for statement 1. Statement 5 says the system AX equal to B is consistent for every n by 1 matrix B. That's statement 5. So assume statement 5. Try to prove for statement 1. We try to prove that matrix A is invertible. That means inverse of A exists. We try to prove that matrix A is invertible, which means inverse of A exists. Next, consider the following column vectors. Let B1 be the column vector 1, 0, 0, 0, 0, 0. B1 has 1 in the first place, the rest are zeros. Let B2 be the column vector 0, 1, 0, 0, 0, 0, 0. B1 has 2 in the has 1 in the second place, the rest are zeros. B2 has 1 in the second place, the rest are zeros. Let B3 be the column vector 0, 0, 1, the rest are zeros. B3 has 1 in the third place, the rest are zeros. And let Bn be the column vector that has 1 in the nth place, the rest are zeros. Consider these column vectors. Since AX equal to B is consistent for every n by 1 column vectors, then the system AX equal to B1, AX equal to B2, and AX equal to Bn then the systems AX equal to B1, AX equal to B2, AX equal to Bn, they are all consistent. By statement 5, they are all consistent. This system is consistent for all n by 1 matrix B. This system, they are all consistent. Consistent means it has at least one solution. If it's consistent means it has at least one solution. So let C1, C2, Cn be the solutions to the above systems respectively. The C1, C2, Cn be solutions to the above systems respectively. Which means C1 is the solution of the first system, C2 is the solution of the second system, and Cn is the solution of the nth system. Then, since they are solutions, if I plug in C1, this equation must be true. If I plug in C2, this equation must be true. If I plug in Cn, this equation must be true. Then AC1 equal to B1, AC2 equal to B2, and in general, ACN equal to Bn. Next, let R1, R2, Rn be row vectors of matrix A. Let R1, R2, Rn be row vectors of matrix A. Then, matrix A can be expressed as R1 in the first row, R2 in the second row, and in general, Rn in the n row. A is an n by n matrix, so it has n rows. Let R1, R2, Rn be row vectors of matrix A. Then A can be expressed as R1 in the first row, R2 in the second row, and Rn in the n row. They are row vectors. What's A times C1? What's matrix A times C1? What's matrix A times C1? Matrix A times C1. Matrix A can be expressed as R1 in the first row, R2 in the second row, Rn in the n row, times C1. C1 is a column vector. C1 is a column vector. When we multiply two matrices, we take row times column. When we multiply two matrices, take row times column. A is n by n matrix. C1 is n by n matrix. C1 is n by 1 matrix. If I multiply the matrix, the result will be n by 1 matrix. A is n by n matrix. C1 is an n by 1 column vector. If I multiply, take row times column. C1 has n rows, 1 column. When I multiply, take row times column. So I get R1 times C1, row times column. Next row, row times column. R2 times C1. And in general, we have Rn times C1. So matrix A times C1 is this matrix. R1 times C1, R2 times C1, in general, Rn times C1. A times C2, similarly, that's R1 times C2, R2 times C2, and in general is Rn times C2. Similarly, we have A times Cn. A times Cn will be R1 times Cn, R2 times Cn, and the last row is Rn times Cn. Here, what's A times C1? A times C1 is B. A times C1 is B. So this column vector equal to B1. A times C1 is B1. That means this column vector is B1. And B1 is the column vector 1, 0, 0, 0, 0. So this column vector R1 times C1, R2 times C1, Rn times C1 equal to the column vector 1, 0, 0, 0, 0, 0, 0. This column vector here, A times C2 equal to B2. B2 is a column vector that has 0 everywhere, 1 in the second place. So this column vector equal to B2. That means this vector equal to B2. R1 times C2, R2 times C2, Rn times C2 equal to B2. B2 is a column vector 0 everywhere, 1 in the second place. And similarly, A times Cn equal to Bn. Bn is a column vector has 1 in the last place, zeros everywhere. Which means this vector R1 Cn, R2 Cn, Rn times Cn equal to the column vector which has 0 everywhere, 1 in the last place. Here, this column is AC1, this column is B1, AC1 equal to B1. This column is AC2, this column is B2, AC2 equal to B2. And this column is ACN, this column is Bn, ACN equal to Bn. Next, let C be the matrix formed by the column vectors C1, C2, Cn. Let C be a matrix formed by column vectors C1, C2, Cn. Then matrix C can be written as C1 in the first column, C2 in the second column, and Cn in the last column. Next, if I multiply AC, what do we get? If I multiply AC, what do we get? A can be expressed as row vectors R1, R2, Rn. A can be expressed using row vectors R1, R2, Rn. C can be expressed using column vectors C1, C2, Cn. If I multiply the matrices, what do we get? When we multiply matrices, we use row times column. Matrix A is n by n matrix. C is also n by n matrix. C has n rows, n columns. If I multiply, the result is n by n matrix. So, row times column. First row times first column, I get R1, C1. First row times second column, I get R1, C2. Then, the last place, first row times last column is R1, Cn. That's the first row. Result is n by n matrix. Second row, R2 times C1. I get R2, C1. Then R2 times C2. I get R2, C2. Continue, I get R2 times Cn. Continue until last row. Last row have Rn times C1. Rn times C2. Continue, Rn times Cn. That's how we multiply AC. Then, what's this matrix? What's this matrix? This matrix, first column, R1, C1, R2, C1, Rn, C1, is a column vector 1, 0, 0, 0, 0. Your first column, R1, C1, R2, C1, Rn, C1, is this column. This column equal to the column 1 with all zeros. That's the first column. What's the second column? Second column has 0 everywhere, 1 in the second place. And similarly, the third column is B3. The third column is B3, which has 1 in the third place, 0 everywhere. And in the last column, that's a column vector, has 1 in the last place, 0 everywhere. In this matrix, we can see that we have 1 in the diagonal. The rest are zeros. This is identity matrix. IN is n by n matrix. That's IN. If A times C is identity, then by the previous theorem, if A times B is identity, then B times A is also identity. Similarly here, if A times C is identity, that means C times A is also identity. By the previous theorem, C times A is also identity. Since A times C is identity, C times A is also identity, then C must be inverse of A. Hence, A is invertible and C is inverse of A. Hence, A is invertible and C is inverse of A. That proves statement 1. Statement 1 says A is invertible. So we assume statement 5 proves statement 1. That means 5 implies 1. Since statement 1 implies 6, 6 implies 5, 5 implies 1. That means statement 1, 5, 6 they are equivalent. Since statement 1, 2, 3, 4 is they are equivalent, statement 1, 5, 6 they are equivalent, use statement 1 as a bridge. All these 6 statements are equivalent, which means if one of them is true, then they are all true. If one of them is false, they are all false. Next, let me remind you of old theorem. Let A and B be square matrices with the same size. If both A and B are invertible, then their product A times B is also invertible. That's a theorem which we learned in the earlier section. Today, we'll study its converse. A new theorem says let A and B be square matrices with the same size. If the product A and B is invertible, then both A and B are invertible. Today we'll study its converse. Let's prove it. If the product of AB is invertible, we try to prove that both A and B are invertible. Let me first of all prove that B is invertible. So, let X be a column vector. Consider the homogeneous system. Consider the homogeneous system. Bs equal to 0. Consider the homogeneous system. Bs equal to 0. By equivalence theorem, by equivalence statement, we know that if the homogeneous system A is equal to 0 has only trivial solution, then matrix A must be invertible. If the homogeneous system has only trivial solution, then matrix A is invertible. So similarly, if I can show that the homogeneous system B is equal to 0 has only trivial solution, then matrix B must be invertible. So here, let X0 be a solution to the homogeneous system Bs equal to 0. I want to show that X0 must be 0. All solutions of the homogeneous system must be 0. Since X0 is a solution, then when I plug in x0, I must get 0. That means x0 satisfies this equation. When I plug in x0, I must get 0. Then b times x0 must be 0. Since x0 is a solution, it satisfies this equation. Now start from here. bx0 equal to 0. If I multiply both sides by a, what do we get? If I multiply both sides by a, I get a bx0 equal to a times 0. On the left side, apply associative law. I get a times b times x0. On the right side, a times 0 is 0. Next, since the product AB is invertible, since AB is invertible, then the homogeneous system ABX equal to 0. Then the homogeneous system ABX equal to 0 has only the trivial solution. By the equivalence statements. Here, we treat AB together as one matrix. If this matrix is invertible, then by the equivalence statements, if this matrix is invertible, by equivalence statements, this matrix times x equal to 0 has only trivial solutions. Since this matrix is invertible, then this matrix times x equal to 0 has only the trivial solutions. That means all solution to this equation is trivial solution. It's the trivial solution. Here, since AB times x0 equal to 0, that means x0 satisfies this equation. Since AB times x0 equal to 0, that means x0 satisfies this equation. So x0 is a solution to this homogeneous system. Since x0 is a solution to this homogeneous system, ABX equal to 0, and it has only the trivial solution, then x0 must be 0. Since x0 is a solution to this homogeneous system, and this homogeneous system has only the trivial solution, then x0 must be 0. Now here, since I prove x0 is always 0, that means the only solution to this equation is 0. Since x0 is a solution to this homogeneous system, and we eventually prove that x0 is 0, that means the only solution to this homogeneous system is the trivial solution. So the only solution to the homogeneous system Bx equal to 0 is the trivial solution. Since x0 is a solution to this homogeneous system, and I prove that x0 is 0, that means this homogeneous system has only the trivial solution. Then since it only has the trivial solution, by equivalence statements, B must be invertible. Then by the equivalence statements, matrix B must be equivalent, must be invertible. By equivalence statements, B must be invertible. So far, we prove that matrix B is invertible. In order to complete the proof, we need to show that matrix A is also invertible. Next, we have to prove that A is also invertible. Since B is invertible, then inverse of B exists. And according to a theorem we learned in earlier section, we know that if inverse of B exists, inverse of B itself is also invertible. Inverse of inverse B is B itself. So if inverse of B exists, then it's also invertible. Inverse of inverse B is matrix B itself. Hence, inverse of B is also invertible. Since AB is invertible, the product of AB is invertible. That's given. Product of AB is invertible. That's the assumption. Since AB is invertible, and inverse of B is also invertible, then how about their product? How about AB times inverse of B? Here we treat AB as one matrix. If I multiply AB, I get one matrix. I treat AB as one matrix. If both matrices are invertible, then when I multiply two invertible matrices, their product is invertible by this old theorem here. If both matrices are invertible, then their product is also invertible. By the above theorem. By this theorem, if both matrices are invertible, then their product is also invertible. Then here, what's AB times inverse of B? Since AB times inverse of B, if I apply associative law, that's A times B times inverse of B. And we know that B times inverse of B is identity matrix. A times identity matrix is matrix A. Since the product AB times inverse of B is matrix A, then A is invertible. Let's complete the proof. If the product AB is invertible, then both A and B are invertible. Let's complete the proof. Therefore, we say both A and B are invertible. So, if both A and B are invertible, then their product is invertible. If the product of AB is invertible, then both A and B are invertible, assuming AB are square matrices. Next, let me introduce diagonal matrix. In a square matrix, if all entries not in the main diagonal are zeros, then this square matrix is called diagonal matrix. If all entries not in the main diagonal are zeros, then this square matrix is called diagonal matrix. Here, let me show you some examples. In this matrix, this is the main diagonal. This is the main diagonal. All entries not in the main diagonal are zeros. This is called diagonal matrix. In this matrix here, that's the main diagonal. All entries not in the main diagonal are zeros. This is called diagonal matrix. Here, this is diagonal matrix. This is the diagonal. All entries not in the main diagonal are zeros. This is called diagonal matrix. And zero matrix is also called diagonal matrix. A zero matrix is also called diagonal matrix because that's the main diagonal. All entries not in the main diagonal are zeros. This is also diagonal matrix. And a 1 by 1 matrix, doesn't matter what it is, a 1 by 1 matrix is always a diagonal matrix. A 1 by 1 matrix is always a diagonal matrix. Next, let's do some computation here. How do we multiply these two matrices? when we multiply matrices, we use row times columns. Let me put 0 here. Here, they are both diagonal matrices. How do we multiply these two matrices? When we multiply matrices, we use row times column. So first row and first column, I get 6. First row times second column, I get 0. Second row times first column, I get 0. Second row times second column, I get 40. That's the answer to this product. Next, let's multiply these two matrices. How do we multiply 3 by 3 matrices? Do the same thing. Use row times column. First row times first column, I get -8. First row times second column, I get 0 plus 0 plus 0, which is 0. First row times third column, I get 0, 0, 0, which is 0. Second row times first column, I get 0, 0, 0. Second row times second column, I get 0, 6, 0, which is 6. Second row times third column, I get 0, 0, 0, which is 0. Third row times first column, it's 0, 0, 0. Third row times second column, it's 0, 0, 0. Third row times third column, it's 0, 0, -10. Now, observe this computation here. Do you see any trick? For these two diagonal matrices, if we multiply the corresponding entry in the main diagonal, what do we get? If we multiply the corresponding entries in the main diagonal, 3 times 2 is 6, 8 times 5 is 40. Let's match what we have here. So, when we multiply two diagonal matrices, if we multiply the corresponding entries in the main diagonal and leave the rest at 0, we get exactly the same answer as we're using matrix multiplication. Let's check this 3 by 3 matrix. 2 times -4 is -8. 3 times 2 is 6. 5 times -2 is -10. Imagine what we have here. So, when we multiply two diagonal matrices, if we multiply the corresponding entries in the main diagonal, we get exactly the same answer as we're using matrix multiplication. That's a property of diagonal matrix. Next, let me show you some properties of diagonal matrix. First property, when multiplying two diagonal matrices, of the same size, we can multiply the corresponding entries in the main diagonal. The corresponding entries in the main diagonal. And leave the rest as 0. Leave the other entries as 0. When we multiply two diagonal matrices of the same size, we can multiply the corresponding entries in the main diagonal and leave the other entries as 0. Hence, the product of two diagonal matrices is also a diagonal matrix. It's also a diagonal matrix. Since we multiply the corresponding entry in the main diagonal and leave the rest as 0, the product is also a diagonal matrix. Next, let matrix D equal to D1, D2. Let D be the matrix has D1, D2, Dn in the main diagonal, and 0 elsewhere. Let D be a diagonal matrix with D1, D2, Dn in the main diagonal, and 0 elsewhere. So let D be a diagonal matrix. D is invertible. If and only if none of the entries in the main diagonal are 0. D is invertible if and only if none of the entries in the main diagonal is 0. And inverse of D is the matrix has 1 over D1, 1 over D2, 1 over Dn in the main diagonal, and 0 elsewhere. Which means inverse of D is also a diagonal matrix. Inverse of D is also a diagonal matrix. When we multiply two diagonal matrices, D times 1 over D is 1. D2 times 1 over D2 is also 1. Dn times 1 over Dn is 1. So when we multiply D and inverse of D, we have 1s in the main diagonal and 0 elsewhere, which is identity. Which means D times inverse of D is identity matrix. Therefore, they are inverse of each other. If none of the entries are 0, if the entries here are not 0, then 1 over D is a real number. 1 over D2 is a real number. If none of the entries are 0, then inverse of D is defined. It is well defined. And when we multiply D and inverse of D, we get identity matrix. Therefore, they are inverse of each other. Next property. Let D be a diagonal matrix of the form of D1, D2, Dn in the main diagonal, and 0 elsewhere. Let D be a diagonal matrix with D1, D2, Dn in the main diagonal, and 0 elsewhere. So let D be a diagonal matrix. Then D to the power k. D to the power k is D1 to the power k, D2 to the power k, and Dn to the power k in the main diagonal, and 0 elsewhere. We know that for D squared, we have D1, D2, Dn times D itself. When we multiply this diagonal matrix, we multiply the corresponding entry in the main diagonal. I get D1 squared, D2 squared, Dn squared, and the rest are zeros. This is again a diagonal matrix. For D to the power 3, we can use D2 times D, which is D1 squared, D2 squared, Dn squared in the main diagonal, 0 elsewhere, times D. D is D1 times D2 times Dn, and 0 elsewhere. Now we multiply these two diagonal matrices. We multiply the corresponding entry in the main diagonal and leave the rest as 0. We have d1 cube. d1 squared times d1 is d1 cube, d2 cube, and dn cube, and 0 elsewhere. So in general, when d raised to power k, we get this. d1 to the power k, d2 to the power k, dn to the power k in the main diagonal, and 0 elsewhere. If this is true for k equal to 0, 1, 2, and so on. K could be any integers. If d is invertible, which means none of the entries are 0 here. None of the entries in the main diagonal are 0. If d is invertible, then the above formula, this formula, is also true when k equal to -1, -2, and so on. If d is invertible, then this formula is also true when k equals to negative integers. If d is invertible, that means inverse of d exists, and inverse of d equal to 1 over d1, 1 over d2, 1 over dn in the main diagonal, and 0 elsewhere, which means inverse of d equal to d1 raised to -1, d2 raised to -1, and dn raised to -1, 0 elsewhere. Then for d raised to a negative power, for example, d raised to -5, that can be noted as inverse of d raised to power 5. Since inverse of d is a diagonal matrix, when I raise it to power 5, I can distribute power 5 to each of them. I get d raised to -1 raised to power 5, d2 raised to -1 raised to power 5, and dn raised to -1 raised to power 5, 0 elsewhere. That's d1 raised to -5, d2 raised to -5, and dn raised to -5, 0 elsewhere. So d raised to -5 is we distribute -5 to each entries. So if d is invertible, the above formula is also true when k equal to negative numbers. Next, let me introduce upper triangular matrix and lower triangular matrix. In a square matrix, if all entries below the main diagonal are zeros, then this square matrix is called an upper triangular matrix. In a square matrix, if all entries below the main diagonal are zeros, then this square matrix is called upper triangular matrix. If all entries above the main diagonal are zeros, then this square matrix is called a lower triangular matrix. If all entries above the main diagonal are zeros, then this square matrix is called lower triangular matrix. Here are some examples. Those are examples of upper triangular matrix. If all entries below the main diagonal are zeros, then this is an upper triangular matrix. If all entries below the main diagonal are zeros, this is called upper triangular matrix. This is main diagonal. If all entries below the main diagonal are zeros, this is called upper triangular matrix. A 1-by-1 matrix is always an upper triangular matrix. A 1-by-1 matrix can always be considered as an upper triangular matrix. Here, those are some examples of triangular matrix, lower triangular matrix. If all entries above the main diagonal are zeros, this is called a lower triangular matrix. If all entries above the main diagonal are zeros, this is called lower triangular matrix. If all entries above the main diagonal are zeros, this is called lower triangular matrix. A 1-by-1 matrix is always a lower triangular matrix. So in general, a diagonal matrix is both the upper triangular matrix and the lower triangular matrix. A diagonal matrix is both the upper triangular matrix and lower triangular matrix. a 1 by 1 matrix is considered to be diagonal matrix. Therefore, a 1 by 1 matrix is always considered as upper triangular matrix and lower triangular matrix. 1 by 1 matrix is both upper triangular and lower triangular matrix. So keep it in mind. A diagonal matrix is both an upper triangular and lower triangular matrix. Upper and lower triangular matrix. Next, let's do some computation about upper and lower triangular matrix. First example, when we multiply two matrices, we use row times column. Row times column, 4 plus 0 is 4. Row times column, 5 plus 12 is 17. Row times column, 0 plus 0 is 0. Row times column, 0 plus 18 is 18. Next example, when we multiply matrices, use row times column. Row times column, 2 plus 0 plus 0 is 2. Next, row times columns, 6 plus 4 plus 0 is 10. Next, row times columns, 4 plus 0 plus 0 is 4. Next, row times column, 0 plus 0 plus 0 is 0. Next, row times column, 0 plus a plus 0. 0 plus a plus 0 is a. Next, row times column, 0 plus 0 plus 6 is 6. Next, row times column, 0, 0, 0 is 0. Next, row times column, 0, 0, 0 is 0. Next, row times column, 0, 0, 2 together is 2. So here, based on these two examples, we can see that when we multiply two upper triangular matrices, the answer is also upper triangular. Let's try some different examples. How do we multiply these two matrices? Again, we use row times column. Row times column. -2 plus 0 is -2. Row times column. 0 plus 0 is 0. Row times column. -1 plus -9 is -10. Next, row times column. 0 plus -12 is -12. Next example. Use row times column. Row times column. A plus 0 plus 0 is A. Next, row times column. 0 plus 0 plus 0 is 0. Next, row times column. 0 plus 0 plus 0 is 0. Next, row times column. 4 plus 3 plus 0. 4 plus 3 plus 0 is 7. Next, row times column. 0 plus 2 plus 0. Row times column. 0 plus 2 plus 0 is 2. Next, row times column. 0 plus 0 plus 0 is 0. Next, row times column. 0 plus 9 plus 1. 0 plus 9 plus 1 is 10. Next, row times column. 0 plus 6 plus 1. 0 plus 6 plus 1 is 7. Next, row times column. 0 plus 0 plus 2 is 2. So here we see that when we multiply two lower triangular matrices, the result is also lower triangular. Next, transpose of this matrix. How do we find transpose of this matrix? For transpose of a matrix, we write rows in columns. For transpose of a matrix, we write rows in columns. So we write the first row in the first column, write the second row in the second column. Next one, transpose of this matrix, we write rows in columns. For transpose of this matrix, write rows in columns. So I put the first row in the first column, put the second row in the second column, put the third row in the third column, Next, put rows in columns. For transpose, put rows in columns. Put the first row in the first column. Put the second row in the second column. Same thing, put rows in columns. Put the first row in the first column. Put the second row in the second column. Put the third row in the third column. So here we can see that the transpose of upper triangular matrix is lower triangular. Transpose of upper triangular matrix is lower triangular. And the transpose of lower triangular matrix is upper triangular. Transpose of lower triangular matrix is upper triangular. Next, based on this example, let me show you some properties of upper and lower triangular matrices. Properties of upper and lower triangular matrices. The transpose of an upper triangular matrix is always lower triangular. The transpose of an upper triangular matrix is always lower triangular. The transpose of an upper triangular matrix is always lower triangular. And the transpose of a lower triangular matrix is always upper triangular. The transpose of a lower triangular matrix is always upper triangular. The transpose of a lower triangular matrix is always upper triangular. Next property. The product of two upper triangular matrices is always upper triangular. The product of two upper triangular matrices is always upper triangular. The product of two upper triangular matrices is always upper triangular. The product of two upper triangular matrices is always upper triangular. And the product of two lower triangular matrices is always lower triangular. The product of two lower triangular matrices is always lower triangular. The product of two lower triangular matrices is always lower triangular. The product of two lower triangular matrices is always lower triangular. Next, let me introduce symmetric matrix. Let A be a square matrix. If A transpose equal to A, then we say matrix A is symmetric. Here we have some examples of symmetric matrices. How do we know they are symmetric? In order to show they are symmetric, we need to show A transpose equal to A. What's A transpose? For A transpose, in matrix A, we put rows in columns. So put rows in columns. I get put first row in the first column, I get 1, 4, 2. Put the second row in the second column, I get 4, 0, 3. Put the third row in the third column, I get 2, 3, 6. Which is exactly the same as matrix A. Which is exactly the same as matrix A. Same thing, how do we know matrix B is symmetric? We find transpose of B. For transpose of B, we put rows in columns. So put the first row in the first column. Put the second row in the second column. We can see that B transpose is exactly the same as matrix B. So we say B is symmetric. How about matrix C? Matrix C is a diagonal matrix. How do we know this is symmetric? So let's find C transpose first. For C transpose, we put rows in columns. So put first row in the first column, I get D1, 0, 0, 0. Next, put the second row in the second column, I get 0, D2, 0, 0. Next, put the third row in the third column, I get 0, 0, D3, 0. Then I put the fourth row in the fourth column, I get 0, 0, 0, D4. That's exactly the same as matrix C. So we say matrix C is symmetric here. Matrix A, B, C, they are all symmetric matrices. If we observe this matrix, we can see that this matrix, they are symmetrical over the diagonal. This matrix, they are symmetrical. It's symmetrical over the diagonal. Over the diagonal, this 4 and this 4, they are exactly the same. This 2 and this 2, they are exactly the same. This 3 and 3, they are exactly the same. So this matrix is symmetrical over the main diagonal. Also, this matrix is symmetrical over the main diagonal. 6 and 6, they are exactly the same. Also, it's symmetrical over the main diagonal. 0, 0, 0, 0, they are exactly the same. So note, if a matrix if a square matrix is symmetrical, if a square matrix is symmetric, then the entries in the matrix is symmetrical over the main diagonal which means A12 equal to A21, A13 equal to A31, A23 equal to A32, which means in general which means Aij equal to Aji. For all Ij with Ij between 1 and n, assume the dimension of the matrix is n by n. Assume the dimension of the square matrix is n by n. So in general, Aij equal to Aji for a square matrix. Here, A12 equal to A21, A13 equal to A31, A23 equal to A32. Here, A12 equal to A21, A12 equal to A21, A13 equal to A31, A14 equal to A41. In general, Aij equal to Aji for all Ij with Ij between 1 and n. Assume the matrix is n by n matrix. And also, all diagonal matrix is symmetrical. All diagonal matrix is symmetrical. All diagonal matrices are symmetrical. All diagonal matrices are symmetrical. All diagonal matrices are symmetric. Next, let me show you some properties of symmetric matrices. Let A and B be symmetric matrices of the same size, and let K be any scalars. Scalar means a real number. Let K be any real number. Then we have the following properties. A transpose is symmetric. A plus B is symmetric. Scalar K times A is symmetric. How do we prove then? How do we prove? So, since A and B are both symmetric, then if they are symmetric, that means A transpose equal to A and B transpose equal to B. If they are both symmetric, A transpose equal to A, B transpose equal to B. We'll use this tool to prove all these three properties. First property, we try to show that A transpose is symmetric. In order to show a matrix is symmetric, we need to show the transpose of the matrix equal to the matrix itself. We try to show the transpose of this matrix equal to this matrix itself. So our goal is to show the transpose of this matrix, equal to the matrix itself. That's the goal. we try to show the transpose of this matrix equal to the matrix itself. Then, if I can show that this matrix is symmetric, so that's the goal. A transpose. In an earlier session, we know that A transpose equal to matrix A. And we know matrix A is the same as A transpose. Since A is symmetric, matrix A is the same as A transpose. So we have A transpose equal to A transpose. Since the transpose of this matrix equal to this matrix itself, then A transpose is symmetric. Let's prove for part A. For part B, we try to show this matrix is symmetric. So our goal is to show that A plus B transpose eventually equal to A plus B. That's our goal. We try to show the transpose of this matrix equal to this matrix itself. That's the goal. To show a matrix is symmetric, we need to show the transpose of the matrix equal to the matrix itself. So that's our goal. Show that the transpose of this matrix equal to this matrix itself. So start from here. A plus B transpose. A plus B transpose. By a property we learned in earlier section, we can distribute transpose to each of them. It's A transpose plus B transpose. And we know that A transpose equal to A. B transpose equal to B, since both A and B are symmetric. So we have transpose of AB equal to AB. That means AB is symmetric. Since the transpose of A plus B equal to A plus B, then A plus B is symmetric. Let's prove for part B. For part C, we try to show that Ka is symmetric. That means we need to show that Ka transpose equal to the inside Ka. That's our goal. We try to show that Ka transpose equal to Ka. So Ka transpose. By a property we learned in earlier section, we know that Ka transpose, we can pull out K. For Ka transpose, if K is scalar, I can pull out K. That's the sense K times A transpose. And we know that A transpose is the same as A, since A is symmetric. So I get Ka here. Since Ka transpose equal to Ka, since the transpose of Ka equal to Ka itself, then Ka is symmetric. That's a proof for these three properties. Next, let's create a theorem. Let A and B be symmetric matrices. Then the product of AB is symmetric if and only if A and B commute. A and B commute means A times B equal to B times A. That's what commute means. So here, this proof contains if and only if. We need to prove in both directions. We first of all assume AB is symmetric and prove that AB commute. Then we assume AB commute and prove that AB is symmetric. So we need to prove in both directions. For if and only if, we need to prove in both directions. Let's prove it. Since AB are both symmetric, since AB are symmetric matrices, then A transpose equal to A and B transpose equal to B. That's what symmetric means. Next, we assume AB is symmetric and try to prove that AB commute. From left to right, assume the product AB is symmetric. I'm trying to prove that AB commute. I'm trying to prove that AB commute. Here, AB is symmetric. That means what? Here we treat AB as one matrix. If this matrix is symmetric, then AB transpose equal to AB. If AB is symmetric, then AB transpose equal to AB. So AB equal to AB transpose. Here we have AB equal to AB transpose. In the earlier section, we know a property about transpose. It says, for AB transpose, if I distribute transpose, I write AB in the reverse order. If I distribute transpose, I write AB in the reverse order. So I get B transpose times A transpose. If I distribute transpose, I write AB in the reverse order. So I get B transpose times A transpose. Since AB and both A and B are symmetric matrices, then B transpose equal to B, A transpose equal to A. So we have AB equal to BA. Here we have AB equal to BA. Then we can say AB commute. Hence A and B commute. Next, try to prove in the other direction. Assume AB commute. Try to prove that AB is symmetric. Try to prove in the other direction. So assume A and B commute. Assume A and B commute. Try to prove that the product AB is symmetric. So AB commute means A times B equal to B times A. AB commute means A times B equal to B times A. We try to prove that A times B is symmetric. If we treat AB as one matrix, in order to show AB is symmetric, we need to show that the goal is to show that AB transpose equal to AB. That's our goal. We try to show that AB transpose equal to AB. So start from AB transpose. Try to show that equal to AB. In the earlier section, we know that a property of transpose says, if I distribute transpose, I run the matrices backward. I run the matrices in the reverse order. That's B transpose, A transpose. If I distribute transpose, I run the matrices backward. Since A and B are symmetric matrices, then A transpose equal to A, B transpose equal to B. So here, B transpose equal to B, A transpose equal to A. Since AB commute, we have AB equal to BA, so BA equal to AB. Since AB commute, then AB equal to BA, then we can say BA equal to AB. So here we prove that AB transpose equal to AB. Since AB transpose equal to AB, then we can say that the product AB is symmetric. Let's complete the proof. Next theorem. Let A be an invertible matrix. If A is symmetric, the inverse of A is also symmetric. Let's prove it. For this theorem, the goal is to show that inverse of A is symmetric. In order to show inverse of A is symmetric, we need to show that the transpose of inverse of A, equal to inverse of A. That's our goal. That's how we show inverse of A is symmetric. So let's start from what's given. Here, what's given is that A is invertible. Since A is invertible, what can we say about A? Since A is invertible, in the earlier section, we know that if A is invertible, A transpose is also invertible. If A is invertible, A transpose is also invertible. And the inverse of A transpose is the transpose of A inverse. That's a theorem we learned in the earlier section. It says if A is invertible, then A transpose is also invertible. And the inverse of A transpose is the transpose of A inverse. That's a theorem we learned in the earlier section. And also, we know that A is symmetric. Since A is symmetric, then by its definition, A transpose equal to A. That's what symmetric means. That's what's given. Next, prove this. Prove the transpose of A inverse equal to A inverse. Let's prove this. So start from left side. Transpose of A inverse equal to inverse of A transpose. Since A is invertible, transpose of A inverse equal to inverse of A transpose. Since A is symmetric, A transpose equal to A. Since A is symmetric, A transpose equal to A. So transpose of A inverse equal to inverse of A. Then since the transpose of A inverse equal to A inverse, then this matrix is symmetric. That's a proof of this theorem.